Howdy, my name is Richard Lawrence. I'm a user support specialist with the High Performance Research Computing Group at Texas A&M University. Today I will be your instructor, and we will be learning about containers for scientific workflows. We will be using the Singularity container runtime on the ACES cluster. Hopefully, when you registered for this course, you provided an access ID, and afterwards we would have created you an account on ACES so you can log in and do exercises. Today we will be talking about containers from the perspective of someone who may have never heard of containers before. So first I'll give an overview of containers conceptually, then I'll talk about Singularity, the runtime, and then we'll get started. We will log in and run our first containers. For the learning topics, I have selected topics that are most relevant for someone who doesn't necessarily want to know everything about containers, but instead you're focused on what do I need to know to do my research? So in order to do your research, you need specific skills, and we'll be focusing on the specific skills that are relevant for people doing research on clusters such as ACES. And that means that we have the luxury of actually getting to try some scientific applications. I have two selected for you today: PyTorch, which is machine learning, and LAMMPS, which is molecular dynamics. I have a slide here about learning resources. The first three bullet points are published by Texas A&M. So we have a course webpage. The course webpage includes this slideshow, which I do recommend that you open up so that you can follow along with the slides in another tab. The reason I recommend this is there will be parts of the course where I ask you to type some code into the command line, and it may be, very long and tedious to type by hand. So copying and pasting from the PDF into your command line could be an improvement. So let's do that together, actually. If I navigate to the hprc.tamu.edu under training courses, the first course is the one that's happening right now. And that's a way to get to the course homepage without clicking so many buttons. Let me make my screen a little bigger. On our course webpage, if you scroll down, you'll see course materials in basically reverse chronological order. So the first one is the latest one. So that's a PDF. So please do open up that PDF. In my browser, it opens up in the browser. You can also download it and open it in a different application if you prefer. That's not really important. So you can see these are the exact same slides that I'm presenting. That means you can follow along to do copying and pasting if you hit some commands that you feel are too long and not worth it for you to type by hand. We have a knowledge base where we document basically everything we know about how to do scientific research. So I have a number of examples of using Singularity in our knowledge base. And so after the course, if you just want to see like the bullet points, what are the main things I need to know, that's a good place to go and look at them. We have a YouTube channel where short courses like this one get uploaded after we teach them. So if you want to revisit this at a later time or learn a slightly different topic, we have lots of videos available. And I'd also like to take a moment to advertise the Access links page. Access curates a set of links that are useful. Many of them have to do with learning. Some of those have to do with containers. So if you want to learn some new skills that are relevant for computing, especially on ACES resources, that's a good place to start searching for your learning materials. Overview of containers. Before I talk about containers, I think it would be fun to ask people, show of hands, go ahead and use the Zoom reaction feature if you have used containers before, perhaps a different container runtime such as Docker or Charlie Cloud. I do see a check mark, a raised hand, a thumbs up. Some people, we got a red reaction. So someone here has never used the containers before. Okay. And that's why we have a section about overview of containers. So for people who've used containers before, this will be familiar content, hopefully. And for the rest of us, I hope it makes containers less mysterious. What are containers? A container is a process that has its own view of local resources. Examples of local resources include the file system, user IDs, the network, basically anything the operating system has control of. For today, we'll be focusing on the file system as the main resource that is of interest to containers, but containers can also work with other resources. So here's an example of a normal process represented by the gear. And the normal process sees a file system represented by the compact disk. But somewhere in that file system, there may be a sector that is itself a representation of a smaller file system. We call that an image. The word image comes from back when disks were literally optical disks, so data on them was literally images. A container would be a process that sees the image as though it were the operating system's file system resource. So it's not aware of the real physical file system. It assumes that image is the real physical file system. Any questions so far about why I'm calling a container a process and why I'm calling this smaller copy an image? Are these words familiar to you? Paul says these words seem familiar. Okay. I think that means we should move on. Why use containers? Containers promote shareability. You can share your container image file by uploading to a public repository, and you can use images shared by others. Containers also provide portability because you can use images on any computer that has the same architecture. An example of an architecture is x84-64. Another example of an architecture would be ARM. Those are the two most commonly found. And containers promote reproducibility, which is a science concept. When you do science, one of the principles of science is future scientists should be able to reproduce your work and agree with your results. If you build software that depends on the current state of the cluster that you built it on, and then the cluster changes because the sys administrators do an upgrade, for example, your build may break, and it may be very difficult for you to reproduce your past work. So by including as many dependencies as possible into your build, you make yourself less affected by changes to the cluster environment. So then at a later time, it's easier to reproduce your work. And containers are one way to achieve that goal. What goes in container images? So a similar concept to containers is the virtual machine. A virtual machine is when you put everything that would normally be on a disk, including the operating system, into the image. So then when you launch a virtual machine process, you have to have a guest operating system kernel running, which means that you have to give that operating system some resources to be in control of, which means you have a virtual machine manager that is emulating hardware for the guest operating system to be in control of. Meanwhile, the real operating system is in control of the real hardware. The downside of the virtual machine should be obvious because the operating system kernel is very large in memory. You can't have very many of these processes running at once on a server. You'll run out of memory. So the idea of containers is, let's not duplicate that operating system kernel. We'll use the real host operating system kernel, and we'll only put things in the containers that make one operating system different from another. So the part of the operating system they all have in common, which is the kernel, is not duplicated. So these containers are much smaller in memory. You can have a lot more of them without running out of memory. So that's great for shared resources like the ACES computing cluster. Popular container runtimes. Containers have actually been around for a while. The first featureful container runtime was LXC in 2008, but aside from some extreme Linux nerds, nobody really knew about it. It wasn't until Docker came along in 2013 that containers really took off in popularity. Docker provides a more user-friendly interface for people who don't necessarily care about Linux that much, but just want to do their research. So across a variety of science fields, many people are still using Docker today. But Docker is not without its problems. For example, it is not designed for shared resources such as HPC clusters. In order to function on HPC clusters, it was necessary to create new container runtimes. So now we have a whole family of new container runtimes that each address the problems of Docker in a different way. One of the first was Singularity. Singularity is very successful, it's still being used, and it's the one we're learning today. But there are others, including Shifter and Charlie Cloud. Podman is a popular container runtime, but it is not designed for HPC. It's designed for other purposes, so we won't be talking about it as much, but it does address problems in Docker. It addresses problems in Docker, but not for the purpose of HPC. So there is one container runtime name that I didn't list on here, which I'm going to talk about in just a second, because I'm going to talk more in detail about Singularity. Singularity is the one we're learning today. Singularity is designed to be easy to use. Similar to Docker, it provides a lot of features out of the box so that you don't have to worry too much about the details under the hood of how containers work. And Singularity is also designed to be a high-performance container solution. So from the start, the user of someone doing research on an HPC cluster was always kept in mind. Singularity's, what do you call these? The motto, the tagline is deploying secure container solutions from edge to exascale. That's basically a lot of buzzwords. And Singularity is produced by a corporation, Scilabs, which is not affiliated to any institution, any educational institution that I'm aware of. So here's the next slide. Singularity is Apptainer. You may have heard of Apptainer. Apptainer is the other container runtime that wasn't on my list. A very brief history of Apptainer. So once upon a time, Scilabs produced a great product named Singularity. No, we can't just have one. Let's make tiers. So they have a free tier, a more expensive tier, extra add-on services, because they are a company and they need to make money. And everyone knows that having different tiers of service is very popular for companies right now. Wait a second. Linux Foundation says, did someone say free? Don't mind if I do. So the Linux Foundation has a fork of the free version of Singularity, which is Apptainer. That's literally what that is. So it's essentially the same code underneath. They just took the Singularity branding off so that they can offer it for free. So on any given cluster, Singularity may be installed or Apptainer may be installed. They're essentially the same technology. It just depends on whether the cluster administrators want to be doing business with Scilabs or not. That's like basically their preference. Let's talk about Singularity features. Singularity is a container runtime and an image builder. That's actually a new feature. In the past, I would have said Singularity is a container runtime only, but thanks to recent developments, Singularity is also an image builder. Singularity can read and convert Docker images. Like I previously talked about, the majority of container users historically have been using Docker. So the majority of container images are in the Docker format. That's no big deal because Singularity can read and convert Docker images. So as a Singularity user, you have access to the full wealth of container images available. For Singularity, the file system inside the container is isolated. So you cannot accidentally break the host file system, nor can other users see your files inside the container. So we have what? Security. That's one of Singularity's principles. The user inside the container is the same as the user outside. That means two things. First, it's simple for you, so you don't have to worry about having a new username. And second, it means a lot of high performance concepts like resource control per process. So a user may have a certain amount of resources that are allocated, and the system may wish to enforce that by telling each process how much resources it's allowed to use. And because you are the same user inside the container and outside, it's not a problem. The normal ways that systems monitor process resource usage still work correctly. Singularity works with high performance cluster technologies. And the reason for this is because Scilabs put a lot of work into making this to be the case. So technologies such as NVIDIA GPUs, InfiniBand network cables are all explicitly supported by Singularity because they know that their customers need those things. You can read more in the Apptainer manual. You could also read in the Scilabs variant of that manual. They're essentially the same thing. I just picked one at random. Let's talk about using Singularity on the ACES cluster. So Singularity is available on compute nodes. That means it is not available on login nodes. And that is because Singularity activities are too resource intense for login nodes. If you are doing Singularity activities, almost certainly you're going to be using a significant chunk of CPUs and memories. And if we're all doing that on the login node at the same time, we're going to bring the login node down. So we need to be on compute nodes where we can each to be allocated a slice of resources, so we're not fighting for those resources. Next, Singularity images can be large on disk. You need to be aware of your storage quota. So if you're going to put a Singularity image file into one of your file air spaces, you should prefer to put it in your Scratch file space because Scratch has a larger quota than your home space. Next, some container activities may be too I/O, that's input-output, intense for the shared network file system. So Scratch and Home are both network file systems on ACES. Under the hood, they're powered by Lustre. Lustre is great for synchronizing file systems across many servers, but it doesn't do so great when you're making lots of little tiny file operations. And so some container activities that involve making lots of little tiny file operations are too intense for the shared network file system. So in order to be courteous to others, and let everyone use the network file system, we will prefer to put your images on the local file system. Every node has a local file system in addition, and that's where we'll do our image operations that are larger. And I will explain to you how to do that as we go forward. So now it's time to do getting started. Does everybody feel ready to do getting started? Let's log into the ACES cluster together and try out Singularity together. So for some of us, that will be your first experience with containers, which is very exciting. So you need to get to the ACES cluster. You can just type in the URL for the ACES cluster, which is portal ACES HPRC tamu.edu. We'll drop that in the Zoom chat. Alternatively, you can navigate to it from our HPRC homepage. So hprc.tamu.edu. The portal menu, the last item in the portal menu is ACES portal, which is just a link to the same thing. Then you need to do your authentication. If you registered for access using an identity provider, which I highly recommend, you'll select it from the drop-down menu, and it will redirect you to your institution's SSO. For example, I'm from Texas A&M, so this redirects me to my Texas A&M Central Authentication Service. Two-factor authentication is enabled, so I have to go on my phone and push the button, and we land on the ACES portal. Let me make my font size a bit bigger. Danishka, that doesn't really look like a link. I was hoping it would look like a link. I would like to know if anybody is having difficulty authenticating to the ACES portal. You may, if your account is not created correctly, you would see an error at this time. It may seem like a cryptic error, and we can help you sort that out. If you get stuck trying to log into Portal ACES, we would like to know so that we can help you. As I want everyone to have a chance to try out Singularity and do exercises with me today. Oh, yes. So this is some screenshots that I previously took. If you do not have an identity provider of your own, ACES CI also provides a more normal looking login prompt, which is nicknamed Xseed because the people using this ones are the same people who previously used Xseed. So if that's what you're doing. Okay, so in order to do today's exercises, we'll be operating in a shell, which is a type of Linux terminal. So in order to get a shell on the ACES cluster, we have the clusters menu with the ACES shell access option. Why it's named this, I do not know. It's simply the one we need for this purpose. If you click on it, it should open a new tab with our message of the day and a shell prompt at the bottom to let you know that you have successfully reached an ACES login node. There are 3 ACES login nodes. If you successfully reach one, please do respond in the Zoom chat which login node you landed on. I expect it will be random. There's like a round robin scheduler that puts you on one so that we don't all end up on the same login node. Ta-da! I landed on ACES login 1. So now that you're on the login node, there are a couple of tasks we can do on the login node. We can set up a space for doing your exercises. Because we will be putting Singularity images in your Scratch area, we need to make a directory in your Scratch area where we will put them. So that's what these commands are. CD to your Scratch area with the $capital Scratch, which is simply shorthand for the path to your personal Scratch area. mkdir, name that directory whatever you like. I named mine S for Singularity _tutorial. and then cd into that directory. So pwd will let you know what is the full path to your Singularity tutorial directory, where you'll put your Singularity image files. Next, we need to remember the location where our training materials are. So I have some backup copies of the training materials in case one of the exercises doesn't work out for you and you need to skip ahead. You can get essentially the solution by just copying the existing material from the training directory into your local area if that comes up. It turns out to be necessary. We don't know yet if that will be necessary. So I named it capital training as just a shorthand so later I can remember where it is. So I can cd to my scratch area. And I actually already made this directory. So in my personal directory, it looks like scratch user, my username, s_tutorial. And there are some files here, and I'm tempted to remove all of them because I was, doing these exercises earlier. Beyond. Okay, now I'm starting fresh just like you. And the next thing I need to do is create this variable that points to the training materials. So because this is a bit on the longer side, this is a good use case for copy and paste. So I'm going to the PDF that I have open in another tab, which you should also have open in a tab. And I'm selecting this path. And I can use my normal operating system hotkey for copy and paste. I'm on Windows, so that would be Control-C. And it works fine with the portal. So then I hit enter, and that just creates that variable. So for example, you can list the files in that directory, and you can see there are some files there, including some Singularity images. So if it comes to later and you don't have one that you need, you can just get a fresh copy. No big deal. Now here's for the tricky part. I previously said that Singularity is available on compute nodes. That means we need to get to a compute node. Since we're going to be working interactively in a shell, we need to know how to get to a compute node interactively. And the language for that in Slurm is called the srun. Srun allows you to execute one command on a compute node, but we can use it to execute the bash command on a compute node, essentially just giving us a shell on a compute node. On ACES, there are 2 Slurm directives that are required for every Slurm job, including interactive Slurm jobs. Those are the time and the memory. So yes, you must specify time and memory. If you don't put a unit on the time, it's minutes. And it is easier to put a unit on the memory because that allows you to just say 4 gigabytes of memory, which should be enough. The PTY flag says we're going to connect your shell session that you currently have to that bash that's going to be running on that compute node. And I does the same thing on the other end. It says that bash should be expecting commands to come over from you. What's the difference between qsub and srun? Srun is for Slurm and qsub is for PBS. Those are 2 different schedulers. The syntax you would use depends on which cluster you're on. I think Slurm is more popular right now, so more clusters would be using something like srun. But there are some clusters out there that are using PBS, and so then you'd be doing qsub, which is just the same thing, but for the other scheduler. I'm not an expert in PBS. It's been a long time since I've used it. So, and one other thing. ACES is a bit busy right now, so it may be harder to get a node. So for that purpose, we have a reservation. And that means you'll have to add the reservation flag to your srun command to use the reserved node. So let me show you what that looks like. If I do srun time equals 120, that's 2 hours. That should be long enough, right? mem equals 4 gigabytes. That should be enough. pty bash I. So if I just say, can I have a compute node, please? I did get a compute node in this case. But maybe you have trouble getting a compute node. So I'm actually going to leave that, and I'm going to say, I want one of the reserved compute nodes. So I'm going to add the reservation equals short course flag. Oh, no, it worked. Okay, so the node AC76, which I had before, this time I landed on AC77, which is a reserved node specifically for this short course. So hopefully AC77 will have space for us to all get on there and do our work. I will copy this command into the Zoom chat in case you want to try the reserved node. Remember, copying and pasting when it looks like multiple lines is a bit tricky. So you either need to widen your Zoom chat until it looks like one line, or copy and paste it a little at a time. Because if you copy and paste multiple lines at a time, you get random results. I would like everyone to take a moment to go ahead and get yourself onto a compute node, either using the reservation or not using the reservation. According to Slurm, the reservation named short course, it has 6 nodes, and a whole bunch of people, that's us, I think, are allowed on it. Now that we're on a compute node, we need to set up our Singularity environment. We want to make sure we're still in our tutorial directory. Now, sometimes Slurm will drop you back into the same directory you were already in, and sometimes it won't, and I don't know why. So just check where you are with pwd. If you're not in your tutorial directory, you need to cd back into it. And then there's 2 more environment settings that we need in order to make Singularity function properly. So the first is we need to give Singularity a cache directory for temporary files. Singularity files are large on disk, and therefore the Singularity temporary files are also large on disk. So we don't want to just put them any old place. It'll fill up your quota. So I would like to put them in the temporary file system, TMP, which is a local file system specific to this node. And Slurm is configured to give each job a directory in the temporary file system, and the variable that points to it is named tempdir. So conveniently, everyone should have a temporary directory named tempdir on the local file system that we can use for our Singularity cache directory. So you need to copy this export Singularity cache directory line from your PDF into your terminal. So I am on slide 20. Export Singularity underscore cache dir equals $tempdir. Okay, so what is tempdir? Tempdir is a directory that has the name of the job that's currently running, and currently the tempdir is empty. Tempdirs get cleaned up after each job so that everybody can continue to use the local file system over time. It doesn't become cluttered up over time. I did see a question I'd like to address. Is this cache directory the image would be saved? Marco asks. No. Some container runtimes, such as Docker and Charlie Cloud, save images in a local image repository. That is not what this is. Singularity does not save images in a local image repository in any way that I know how to work with them. Instead, the cache is for temporary files, and the default workflow in Singularity is you should always build an image to a specific location on disk and not just rely on the cache. The cache is not assumed to exist outside of the moment that you're using it. So we will be saving our images to specific locations on disk when we're ready to do that. And then the final element of setting up your environment is we need to connect to the internet. By default, compute nodes are not connected to the internet. So when we go to fetch a container from the internet, it's going to say, I don't know how to find that. Therefore, we need a web proxy. A web proxy is just a couple of environment variables with some IP addresses, but we provide a module named web proxy that just sets those variables so your compute node can find the internet. So module load web proxy, and now you have the IP addresses set as variables so that your compute node can find the internet. And that's it for setting up the Singularity environment. Now we're ready to use Singularity. So the simplest way to launch a container in Singularity is to use the Singularity shell. Singularity shell will launch a shell terminal, which will be a containerized shell terminal. In other words, it will see the images file system instead of the real physical file system. So that means we need an image. So you tell Singularity that we want to fetch an image from the internet and also launch a shell process that sees that image as the file system. In other words, a shell in that container. And the syntax is you provide first the format of the repository. So this is going to be a Docker repository. And then next, you provide the name of the image in the Docker repository. So this one is named Alma Linux, and then :8. We'll talk more about the bits and pieces of this on a later slide. For now, it's just a simple example. Docker : / Alma Linux :8. I do recommend typing this one by hand because you will have to get comfortable with Singularity syntax over time, and this one is not so difficult. So Singularity, remember tab autocomplete is your friend, shell, space, then the name of the image we wish to launch the container from. In this case, we're going to fetch it from the internet. We're fetching it from a Docker repository, and its name is Alma Linux :8. And we will talk about that. We'll revisit it, I promise. So when you hit enter, it says getting image, does some downloading, creates a file. It does take a moment to create this file. That's because these operations are resource intense, which is why we are not doing them on the login node. And now I have a shell prompt, but my prompt changed. Instead of username @node $, which is what it was before, now it's Singularity caret. It is still a prompt for a shell terminal, but now instead of seeing the real physical file system, this one sees whatever files are in that image. So as an example, here's a file that is in that image. This image has an etc. Red Hat release file. Yep, there it is. Let's read it. This image says that it is an Alma Linux release 8.8 Sapphire Caracal. Marco is asking if this image is in the cache. Yes, that's correct. This image is in the cache, but we can't do anything out of the cache right now. Singularity is completely in control of the cache. So when we're ready to save images, we have to put them in a specific place on disk. We can do that. We will do that later, I promise. So after you're done exploring the file system, we have to feel done. So at some point you're done exploring this file system and you use exit, which is the standard shell way of saying I'm done with this shell. And that closes the shell that's running in the container, and we return to the shell that's on the compute node with the regular compute node file system. For curiosity, does the regular file system have an etc. Red Hat release file? It does, but that file has different contents. We are running Red Hat Enterprise Linux release 8.6 UTPA. That's a fun word to say. So what we have learned is this command, the Red Hat release file, has different results depending on whether the process sees the real physical file system or if it sees the image, which has different files. Joe would like to know, how do I find out if I am in Scratch Drive? So that, hit it with the PWD. Print working directory, and that'll let you know where you are. Congratulations, welcome to containers. I saw at the beginning when I asked that a few of us have never used containers before, and that's not true anymore because now you've used a container and you've seen that the files in the container are different. So that's really exciting. I'm very excited to welcome each and every one of you to the wonderful world of containers. Animation provided by funimata.com, apparently. Were there any questions about that Alma Linux container? I did see someone said, where can we save the Alma Linux container? One of the very next things we're going to do is learn how to save these images. So we can save that Alma Linux image if you want to. That's something that's a possibility. Another thing we can do is talk about where that image came from, if you want to do that as well. We're not quite ready to do both of those things, but we will do them when we're ready to do them. Okay, we will do those things as we learn the necessary elements, which is very soon. Container image sources. So there are repositories on the internet where you can find container images. The most popular is Docker Hub. That's because it's been around the longest, because Docker was the first popular container runtime. So if you do not provide a URL for an image, most container runtimes will assume you mean Docker Hub is the source for that image. If you wish to draw an image from a different repository, you simply provide the URL for that repository. So other repositories include Singularity Library, NVIDIA GPU Cloud, Quay.io, which is similar to Docker Hub, but it has more features if you're really into being a container developer, and Biocontainers, which is a curated repository of containers for biologists. And I have examples in our knowledge base on how to use each of these, because they all involve having a slightly different URL. Today we're going to take a look at Docker Hub. So this example, Docker Hub, is similar to GitHub in that repositories are organized into groups. So each image repository will be group/name. And then within each repository, each image is identified by a unique tag. And so if you're referring to a specific image in the repository, it's group/name:tag. So for this screenshot, I took a look at the Jupyter/SciPy notebook repository, which is a repository of images of Jupyter notebooks with SciPy also installed. So all you have to do is go to Docker Hub and search for Jupyter, and you should be able to find this. And then on the page, I have clicked over to the Tags tab to see how many tags there are. One of them is named Latest, but of course, whenever you pull from Latest, you don't know if you're getting the same thing you got before, so it's generally recommended to specify a tag by its name or number rather than the word latest. So how do we fetch images? If we wish to fetch an image and save it, rather than just using it one-time use, then we can use the Singularity pull command, which fetches images from repositories, converts them to the Singularity file format, and also saves them on disk. The target file name is an option. If you do not provide a target file name, then you will get one by default. The source is required, and it refers to something on the internet, so that will be the one including the URL that we need to talk about. So for Docker images, the source argument looks like Docker : meaning we're going to be pulling an image that's from a Docker format repository. That doesn't mean Docker Hub. There are multiple repositories that come in the same format as Docker Hub. But if you put Docker and no URL, it will assume you mean Docker Hub. So if you're pulling from Docker Hub, you need Docker : / you don't write a URL, you simply provide the group name tag, and you will get an image from Docker Hub. So therefore, the pull command for the Jupyter example on the previous slide was Singularity pull Docker : / Jupyter SciPy notebook latest. Please do download this image now or copy the one that I have in the training directory, because we'll be using this image for an exercise later. Since we didn't provide a file name for the optional argument, it's going to choose for us, and what it's going to choose is the name _ tag .sif. And we'll talk about what that .sif means later as well. Marco asks, how can you find if a Docker image was built with MPI or OpenMP or other library? That's a tricky one. I don't actually know. Many container repositories will have a description element for each image, and then the developer may choose to write, here's what I put in this image, and then a bullet list. But that's a choice each developer makes as to what they're telling you what they put in there. Can you show real quick how to copy from training? I will show you how to copy from training. So if you wish to do the download, you just type this or copy it out of the slides. Hopefully everyone can figure out how to do that. So I have been asked to show the alternative. So we're currently on slide 27. So you either go copy paste this line. Why am I struggling? Copy paste this line into your terminal. Or we can copy the one that's in the training directory. So recall we created a variable named training, and in training, there's the SciPy notebook 2023.sif. So I could do cp training SciPy notebook 2023.sif space dot means the current directory. And now I have that in my current directory. And if you don't like the name, you can always rename it. So you could like MV and then just give it a different name. I'm making it match how it looks in my slides. So if you did the Singularity pull command, it would go fetching blobs, creating SIF, and then eventually you'd end up with this same file. Did anybody try to do the Singularity pull method? I think this one takes a few minutes because it is a bit larger. There's some scientific software installed in there. SciPy. Have you heard of SciPy? Anybody here familiar with Python coding? It does take a couple minutes to pull this one. Yeah, it does take a couple minutes because it is a bit larger. But hopefully we will have enough time for everyone to do that who wants to do that. Oh, another thing is I recall someone said, let's take a look at where that Alma Linux comes from. So I promised we would take a look. So let's go to Docker Hub and read about Alma Linux. So we go to Docker Hub and we search Alma Linux. You can see that there's a repository named Alma Linux, which is a Docker official image. And if we click on it, in the URL, you can see that it has group under group/name, but the group is underscore. Underscore represents the non-group. So because Alma Linux is published by Docker itself, it isn't in a group. So underscore takes the place of that, which is why we didn't need to specify the group when we executed our Singularity shell command. Essentially, Alma Linux is just a small Linux distribution that's based on Red Hat, but doesn't have a lot of files in it. So it's quick. It's a small on disk, and that makes it really useful for building container images because you don't need everything in the kitchen sink every time. It's better to save disk space and just have the basics. So that's what Alma Linux is for. Marco says, can you put Docker inside of Docker? Last year, I would have said no. That was impossible. This year, I have heard a rumor that it is possible. Someone has put Docker in Docker. You can also do things like put Charlie Cloud in Charlie Cloud or put Docker in Singularity and other combinations. I don't know how they do that. It's still a mystery to me, but I have heard that it is possible. Generally, there's not really a need to do that because once you're in a container, you're already fully in control of what's in the container. So putting a container in a container is kind of redundant. It's rarely a use case for that. I have seen some use cases, but they're rare. A more common use case for multiple containers is to have multiple containers side by side. So if you have two softwares that need to work together, but they have different dependencies, you don't have to put them both in the same container. You can put them in their individual containers. So you have two smaller containers and then tell them to talk to each other. That's a more common use case. And I remember somebody else asked, can we save that Alma Linux image? Yeah, we can. So as a quick exercise, I'm actually going to do that. So let's use Singularity pull Docker : Alma Linux :8. And it says using cached SIF image. And if I hit ls, you can see that Alma Linux 8 now appears in my Scratch directory. So Singularity pull now has saved this image in my current directory as a regular file, but it didn't pull it from the internet. It said it used it from the cache. So Singularity is smart enough to know if you execute the same commands to fetch an image that it already just fetched a minute ago, that it doesn't need to do that. It uses the data it already has in the cache. So now we have a copy of Alma Linux in case you need it for later. I don't remember if we need it. Maybe you just want it. That's fine. At least now you know how to do that. When you log out of the compute node, the SIF images get removed. So there are two file systems here. We have the temp file system, and we have the Scratch file system. The Scratch file system is a network file system, so that's available on every node, including the login nodes, and it does not get cleaned out. So these images that are in the Scratch file system will stay there until you decide to delete them. However, the temp space is node specific, and these job directories are managed by Slurm. So when your job ends, they will get cleaned out. So it's a good place to put temporary files, not a good place to put files you want to save for later. And that's why we have two different places on disk where we're keeping files today. Were there any more questions about these image files? Actually, we're going to learn more. When you delete, do you delete images? Yeah, you can delete the files with RM. So they're just regular files. So these right here are just regular files. That's one file. So you can remove it with RM. Over here, you've got the Singularity cache, which is a bunch of files. So you would do something like recursive RM if you wanted to clear it out, or you could just let Slurm do it for you by ending the job that's running. I'd like to talk some more about what we can do with images. So far, all we know how to do is save them, which is a start. Let's learn some more things we can do with images. The Singularity has two image formats. The first is the directory image format. We haven't seen that one yet. So the directory image format is essentially the native format for images, which is just it's the files in the file system in the form that they would look like in the file system, but underneath a parent directory instead of at the root directory. That's what that is. And then we have the single file format, which is where you like all those files together into a single file. There's more than one way to do that. Singularity uses the SIF format for Singularity file images, which is the default. And the Singularity build tool can convert images from one format to the other. If you wish to create a directory format image, then you use the sandbox option. The sandbox option says, I'm going to create an image in the directory format. So what do we need to know? We need to know that, oh, hey, remember somebody was like, can we pull that Alma Linux and save it? Yes, we did need to do that. So if you haven't had a chance, you can pull the Alma Linux now. Go ahead and save it. I named it almalinux.sif in this example. Doesn't matter what you name it, just name it anything. The point of this exercise is to use Singularity build. So note that the order of the arguments is a bit strange. The source comes last and the target comes in the middle. This mimics what the syntax was for Singularity pull. So it's Singularity build sandbox target then source. So if the source is a SIF file, then the target will be a directory. Where do we put the directory? Well, we can't put the directory in Scratch because these images have like thousands of files. And Lustre doesn't do great when you want to read and write thousands of files. So if we all do this at the same time in the Scratch directory, Lustre is going to come to a crawl and we're all just going to have to sit there and be sad. So we're going to be using the local file system in the temp dir. We're going to put the directory image there instead. So some people say that pulling the SIF image, that Jupyter one we needed, has finished. That's good because we're about to do the next exercise. We need to get that Alma Linux in the SIF format and then get it into the directory format. So let me hop on over to my shell and let's do that. So I have Alma Linux _8.sif. I previously did Singularity pull. If I wanted to give it a different name, I would just put the name I wanted it to have after the word pull. And now I have two copies of it, but the other one has the name that I chose. And now we want to do Singularity build. And we want to build a directory image. So we provide the sandbox argument option. And then we have to provide a location where we want it to go. So I'm going to put it in tempter. And I'm going to give it a name, Alma Linux. You don't put a file extension because directories don't have file extensions. And then we need a source. So almalinux.fis will be the source for this build operation. So we're turning the SIF into a directory. And it says, okay. And then it says, here's where I put it. Let's investigate that. What does it look like? It looks like a file system. It looks pretty much just like the file system did when we were exploring Alma Linux earlier. Except now the files are exposed to you. You can see them. There they are. They're just regular files now. Marco, did you do a copy and paste out of my... Oh, I see what happened. So when you copy and pasted, it looks like you got the long dash. It's supposed to be two short dashes. It's supposed to be two short dashes. Oh, it happened again. Man, every time I do this, it's supposed to be 2 short dashes, but every time I do this, a few long dashes end up in the PDF file by mistake. So you had to delete that long dash and make sure it's 2 short dashes. Apologize for the inconvenience, everyone. It didn't happen to me because I typed it by hand. I didn't do copy and paste. So these little tiny bugs that slip through my fingers. Was everyone able to make the directory format image? So what's the point? You may be saying, Richard, what's the point? Why do I want to see all these little files? The point is that directory format images are writable. We can edit them in place. So let's do that. You simply add the writable flag to any container command. So far, the only container command we know is Singularity shell, launching a shell from an image, and then we can play with it. So we add the writable flag to let Singularity know we would like our container process to have permission to edit the image that it's running out of. So Singularity shell -- writable, and then the path to that directory image. And then let's edit it. So one thing you can do to an image is add things to it. So I did mkdir and then add something at the root level. Now, adding something at the root level would be pretty scary if you were on the real physical file system, because that's owned by the root user, which you are not. But in the container, they're just regular files owned by you. So it's no big deal, right? You can edit regular files owned by you. So that's the power of containers. It allows you to do things that you would normally need to be an administrator to do, like put files at the root file system in the container. And then we need to check if the changes are still there. So after you exit the container, you should be able to go back in and see if your changes are still there. And they will still be there because the point of the writable is that the changes are persistent. So let me go ahead and do that exercise, and please do along, and we will ask you how it went. Singularity shell, the name of the image. The image is located at temp_dir Home Linux. And let's create some stuff. So mkdir Richard is cool. Oops, I made a mistake. Can anybody tell me what mistake I made? I'll give you a hint. It was on this line. I forgot writable. Yeah. So I need to exit my container and try again with the writable flag. And then I can make Richard is cool. And I can exit the container and I can go back in. And by the way, when you go back in, you don't need the writable flag if you're just going to look around. And you can see my Richard is cool directory is still there. So, and although I didn't include it as an exercise in my slides, another thing you can do is we can then convert this directory format image back into a Singularity image file format image. Singularity build, except this time the target will be the target will be a .sif file, and the source will be that directory format image. Oh, I'm not familiar with that error. I'm guessing here. I'm hoping this works. Well, it did better than before. So I didn't actually include this as an exercise, so I forgot the syntax. Can you install in the writable shell? Yes, you can do like yum install, for example. If it's a Red Hat-based image, since Alma Linux is a Red Hat-based image, you could do run install. You could do yum install. However, for that particular operation, you would need the fake root flag, which I have on my screen here, but I didn't explain it. We're not going so much into detail about how to build things today. just kind of showing that it's possible. This is the general workflow. So if you want to do something that normally would require root permissions, you may sometimes need to add the fake root option in order to persuade the container to do the thing. Now, it literally does have permission because the literal files on the real physical file system are just owned by you. But in the container, your process may not know that. So you have to trick it into doing its job. And that's what fake root is for. Fake root says, yum, yes, you really are the root user. Now do your job. And as soon as it tries, of course, it's going to succeed. But you have to persuade it to try. So that's what the fake root is for. Sometimes it's necessary when you're building images. You can see I needed it here. So if I look at my almalinux.sif, Singularity shell, my almalinux, you can see the Richard is cool directory is still there. So now I have a flat image file, flat meaning it's a single file on disk that contains my previous edits. We're not going to be doing anything with that today, but I did want to show you that it's possible because sometimes researchers do need to be able to edit these containers, make small changes, just a little tweak here and there, and them giving you the general overview of how that's done. Oh, it would appear that that was an exercise, so I'm incorrect. I said that we weren't going to do it, but my intention, it looks like I previously thought we were going to do this. But then I forgot the fake root flag, so this is broken because you needed the fake root flag. Would anyone like to take time to do this where you convert it to a flat image file and check to see your files are still there in the container image? You just need to add the fake root flag. Let me go ahead and sorry about the cough. I am sick today. Let me go ahead and paste that into the Zoom chat in case anybody wanted to try along. But watch out for those long dashes. They sometimes sneak in there. So does anybody want some time to play with this, or do you feel like you want to move on? Remember, the goal was to get all the way to research today, research workflows, scientific things, and we haven't gotten there yet. So we do need to keep moving if we're going to make it to those scientific workflows. All right. Marco suggests moving on. If you previously attended any of my container courses, you probably are reasonably familiar with this part because we did this before. So we're not going to play with this one anymore at this time. We can play with it later. You can go watch videos the previous times that I played with these things. Let's learn about working with containers. That is, working with container processes, not images. So we're done working with images for now. Now we're going to say, given an image, what can it do? So Singularity has three methods for launching processes. We have the interactive method, which is Singularity Shell. That's the one we already tried. Singularity Shell essentially launches a bash terminal. The bash terminal thinks the image is the file system. We also have the batch processing method, which is Singularity exec. So that's where you just type any commands. It could be shell commands or executables that exist in the container, and it will execute them, and then whenever it's done, it immediately stops the process. So that's not interactive. Singularity exec is for when you are primarily for when you don't want to be typing in one command at a time, but instead just do the whole thing at once. And then finally, we have container as executable, Singularity run. So some developers like to have a standard command that their container is meant to run, and then they kind of make the container image itself be just a wrapper around that command. So then Singularity run is run whatever the default command in the container is. So the container itself becomes an executable. Let's take a look at that Singularity run because it is a bit funny. Let's do Singularity run first. So Singularity run will execute the default run script if one was defined. And if there is one defined, you can also execute the container image as though the container image were an executable. So Singularity run and /container image, they mean the same thing. So here's an example of a container image that has that property, the hello world image from Docker Hub. So let's execute together as an exercise, Singularity poll, docker:// hello-world. It only takes a split second because it's a tiny image. Then you do Singularity run, and then the name of the image file. So by default, it's going to be hello world _latest.sif. It prints out a bunch of words, but among those words, it says hello from Docker. And the alternative method, you can go /hello world sif. It does the same thing. So this is just showcasing this strategy of executing from containers. This is if the developer chooses to define a default run script. You're not really in control of that. It may or may not be the case. Singularity pull docker:// hello-world. That was quick. Singularity run hello world latest. Hello from Docker, and also lots more words. You can also hit it with the /hello world latest.sif. Does the same thing. Let's go to Singularity exec. So Singularity exec lets you access executables and other commands in a container. So this is most appropriate for batch jobs. So whenever you're writing your batch scripts, that's like multiple commands in a file, Singularity exec is the method you would most likely be using. Okay, so an example of an executable that can be in a container is Python 3. Now, ACES nodes already have Python 3, so let's check. Yeah, so ACES nodes have Python 3. It's 3.6.8. But what if we don't want Python 3.6.8? What if we want a different Python? No big deal. You can just get a container image that has Python. In fact, we already have one of those. We have the SciPy notebook image that we downloaded earlier. That definitely has Python in it, right? Let's see. I have one right here. So let's do Singularity exec SciPy notebook latest.sif, and the command we want to run will be Python 3 -- version. It's the same command we just ran on the compute node, but now we're going to run that command in the container. So instead of looking for Python 3 on the real physical file system, it's going to look for Python 3 in the image. And it finds Python 3.11, a different version of Python. If you are copying and pasting, we are currently on slide 36 from our PDF. What's next to learn? Next up on my agenda, working with files. We previously learned that the file system inside a container is isolated from the real physical file system. But sometimes you need files from your real physical file system. So for that purpose, we can mount parts of the real physical file system into the container. By default, Singularity will mount the home directory and the current working directory if it can. You can specify additional directories using either the Singularity bind path environment variable or the -- bind command line option. So let's take a look at an example. So on ACES, we recommend that you mount Scratch so you can get access to your data storage, and the temp file system so you can get access to the local disk on the node. So if you're inside the container and you want to save a file either to the network file system in Scratch or to the local file system in temp, those will both be present in the container so you can use them correctly. So in this example, I'm going to save a file into the temp dir. I'm just going to create a little directory there, but I'm going to do it inside the image in the container, and then I'm going to exit the container and see if it is there in the real physical file system. You can use any image for this purpose, because all we're doing is just making a directory, and all the images, except for Hello World, you can't use Hello World for this. All the images other than Hello World can do this, so just pick one. But watch out for the quotes, because when you copy and paste quotes out of a PDF, sometimes it does not work correctly. I'm nervous about this because sometimes it doesn't work. So I'm going to pick any image. I'm going to pick the Alma Linux image. Yeah, it said it didn't like those quotes. So we're going to have to replace those quotes with normal looking quotes. Okay, so now I have a container. And what's in the container? We have a temp file system and we have a scratch file system that are both present in the container. So we can make a directory, say, in the temp dir for this job. We can make a directory in scratch s_tutorial, my scratchy dir. We can exit the container, and we should be able to verify that both of those things are definitely present on the real physical file system. Yep. So outside the container and the real physical file system, both of these directories now exist. So using the bind is how we can get access to the real file system even inside the container. Although, disappointingly, I do need to admit that Singularity on ACES already binds these directories by default, so we didn't actually need to do this by hand. But maybe you won't be using ACES every time. Maybe tomorrow you'll go use a different cluster and you need to know how to do this. So that's why I'm teaching you. Let's take a look at a Singularity batch example. I said that Singularity exec was primarily for batches. So here's an example of a batch file that someone might use to do a Singularity task. This is a slurm batch file. So we have slurm directives up here. sbatch, time, sbatch, mem. We saw some of these earlier. These are the same directives we used with srun. They are also used in slurm batch files. After you've, got your batch directives, then you start having your script, which is a regular bash script in this case, because at the top it's bang bang bash. So the first thing we needed to do was export the Singularity bind path. So in this case, I'm using the bind path method instead of the -- bind argument. We're using the bind path environment variable. Does the container see all the environment variables? It will see most of them. Shan Ho Tsai. It will see most of them. There are a few. So there's like two categories. There's a handful of special variables that Singularity will not pass into the container because you need to be able to tell if you're in the container or not. If you can't tell if you're in a container, you could get confused. So there are a few that it won't pass in. And then there are the ones that the container itself provides. So LD library path is a good example of this. When you install software in a container, often that software comes with, now you have to set the LD library path. So when the container sets a variable, it will override whatever was outside the container. But the variables that don't have to do with the software that is installed in the container, things like temp dir and home, those just get passed in from the outside correctly. Okay, so I was going to finish talking about this batch example. So in this batch example, we're executing two containers. First, we're doing Singularity run, and then we're doing Singularity exec. And both times we execute, the binding will occur because the variable still exists in memory throughout the rest of this batch script. So that's an advantage of putting the variable, is you don't have to type it more than once if you are executing more than one command in a script. In this case, Singularity exec scipy notebook latest.sif, the command we wanted to run with Singularity exec was python3 hello.py. So the question is, where is hello.py? Previously, you would have had to have put hello.py in the container. But now that we are using Singularity bind path, and we know that we can mount file systems outside the container, hello.py can actually be on the real physical file system. For example, it could be in the current working directory. If hello.py is in the current working directory, then when Singularity launches this process, it will mount the current working directory, and then Python 3 in the container, we'll be able to find hello.py in the current working directory. So if you have some scripts that you need to edit repeatedly, they don't have to be in the image. Do we need to load any modules? That's a good question. On TAC, you do need to load modules. On ACES, you do not. That's kind of a personal preference for the system administrators. TAC installs Singularity in a module, so you do module load Singularity. ACES, the Singularity is installed on the bare metal of the compute nodes, so you don't do module load Singularity. It's just the administrators have to tell you how they did it. Let's talk about interactive graphical computing. So I created this cool idea, which was, suppose you're a Python user and you want to write some Python code. Do you like working in Python script files? Probably not. You probably have a favorite IDE. Many people like Jupyter Notebook. Can you develop your Python scripts in Jupyter Notebook, but also at the same time be using containers? Yes, you can. So here at ACES, we have an interactive app for Jupyter Notebook that actually supports the use of containers. So let's do that example. If we pop on over to our ACES portal homepage, you can find the Jupyter Notebook option under interactive apps, and you can follow along with me. And oops, I previously put PyTorch here, so it autofilled. So you would just go scratch s_tutorial or wherever you put yours, SciPy notebook, latest, or whatever you named it. And yes, oops, spelled scratch wrong. And yes, it's okay to have a variable here because this variable doesn't get expanded by on demand. It just goes into the job script for the interactive job, and it gets expanded on the node that launches the job. So Scratch exists on the compute node. It will get expanded to your personal Scratch directory at that time. And then you pick a node type. I don't know what kind of nodes are available right now. Sometimes the A30s are available, so that's why I have it on A30. That doesn't matter for this example. I just have to pick one and hope it works. So I picked CPU only. And once again, if you don't have one in your Scratch directory, you can use the backup copy, which is Scratch Training Singularity SciPy Notebook _2023. I named it 2023 in case I end up teaching this course at a later time. We will realize that it's not fresh anymore. It won't be fresh in the future. So once you click launch, you have to wait for your job to start. Hopefully it does. Oh, good, it did. So now it says running, and I have a connect to Jupyter button. So you can just open any Python notebook or make a new one. Yeah, so if you click new notebook, you can make a new one. It's up here, new notebook, but I already have one, so I'll just use it. You clear all the cells again. I forgot how to clear all the cells. There we go. So SciPy includes the NumPy. Well, where is it? It's installed at opt_conda lib Python 3.11. Recall Python 3.11 is installed in the container. And Python is installed in the conda area. So apparently, whomever built this used conda to install Python. Is conda where Python is installed on outside the container? I don't know. Let's check. No. Outside the container, Python is installed at USR bin Python 3. Inside the container, it is installed at opt_conda bin Python. So That's how we know for sure this Jupyter notebook is running out of the container. Are there any questions about this? Did you manage to get a Jupyter notebook running? I'm actually going to close my Jupyter notebook now, so that in case other people need to use that node, I don't need to leave it running. I see a question. How would you launch the Jupyter notebook in the container from the command line? That's a bit trickier because if you launch Jupyter notebook from the command line, you would then have to like open a browser and then tunnel to that node. And that's the extra steps, which is possible. And some people do that. I've seen it. I just don't have time to do that for you live right now. So the syntax would actually, I can sort of show you. If you go to the log for the job, which if you click on the job's interactive job name, it's actually a shortcut for going to where this log was. And if you go to the output, you can actually see what command was run. So it was Singularity exec, name of the image, Jupyter notebook, and then the Jupyter config file, which was here, config.py. So yes, this is how you would launch Jupyter notebook from the command line. But the config file is where the magic happens, because that's the thing that's enabling on demand to connect your browser to the Jupyter notebook running on a compute node. If you're not so familiar with Open on Demand, this may be very mysterious as to what I'm even talking about. But if you're familiar with Open on Demand, I think this is very cool. That's actually the end of my like quote unquote normal activities for Singularity. Now we need to talk about those scientific applications. I did promise we would be doing some scientific applications today, because this is containers for research something, whatever I titled this class. ACES is a test bed, and primarily what ACES has is different kinds of GPUs, including NVIDIA GPUs. NVIDIA GPUs have been around the longest, so they're the most well-supported with Singularity. Other types of GPUs we anticipate will be supported, but they're still new enough that I don't have good quality training materials for that purpose. So I'm only able to train you NVIDIA GPUs today. Nevertheless, we can see how to use the fancy, exciting NVIDIA GPUs that are on the ACES testbed cluster. So in order to use containers with NVIDIA GPUs, the container image needs to have been built using a CUDA version that's compatible with the local GPUs. So for most of the GPUs, that's CUDA 11. If you wish to use the H100s, I think the H100s actually require CUDA 12. Now, building container images is generally the responsibility of experts. And who is the expert in building NVIDIA container images? Well, that would be NVIDIA, of course. So we are going to be looking at NVIDIA Cloud as a source of GPU-ready images. And I'll show you what that looks like on the next slide, I think. In order to use an image that is GPU-ready and connect it to the local GPUs, you simply add the --nv flag to your Singularity command. And what that does is it instructs the Singularity to bind mount all of the local GPU drivers from the compute node into your container. I don't even know where they are on disk. I assume they're somewhere in like opt or etc. But Singularity knows where they are. So if you just say Singularity, I need those drivers, it will bind them into your container, and then your software can operate the local GPUs correctly. So here's an example of in the NVIDIA container registry. First, we're going to look at PyTorch. So PyTorch is a popular framework for machine learning, and NVIDIA builds PyTorch to be GPU ready in containers. So if you go to the NVIDIA container registry and search for PyTorch, you end up on a page like this one. It tells you what's in the container and it tells you how to use it. The documentation is quite good. I'm very grateful to NVIDIA for all the work they do to have good quality containers. Now, what do we need for our exercise today? We need to know how to get these containers. So I previously said if you're pulling a container from Docker Hub, you don't need a URL because Docker Hub is the default. The NVIDIA container registry is outside of Docker Hub, so we do need a URL. How on earth does anybody remember these URLs? No big deal. Every single container page has a little button somewhere that tells you the URL. So here we have get container, and you click on it, and it pops up, and there's the exact URL that you need. nvcr.io. That is the URL for the NVIDIA container registry. And then for this particular container image, it is in the NVIDIA PyTorch repository :23 blah, blah, blah. So you just copy that. Warning, do not attempt. This file is 9 gigabytes large, and it took me like an hour to pull it yesterday when I was preparing for the course. So you're just going to be using the one that we have on disk. Please do not attempt to pull your 9 gigabyte file live during the course. You will not make it. But in theory, this was what it would look like. You would do Singularity pull. NVIDIA container registry is in the Docker format. So you say Docker : and then // and then the same URL that the container registry suggests to you. nvcr.io / and then all the rest. I do see someone in chat is saying if the cluster has CUDA 12 and the container CUDA 11. It is not relevant what the cluster has installed. What is relevant is how the software in the container was built. So the container, an old container will not work with newer GPUs because an old container will have a version of CUDA in it that is not aware of newer GPUs. In order to use newer GPUs, you do need newer container images. So let's take a look at our PyTorch GPU exercise. I have sort of concatenated this exercise onto a single slide. What's important? What's important is that the file we need is in our training directory. Scratch training Singularity, which we named $training for short. And the image name is PyTorch _2309-py3.sif, which is the most recent version of PyTorch that I found on the container registry yesterday. CUDA is included in the container, but the drivers are outside the container. NVIDIA makes the split on what lives in the container at the driver level, usually. So the NVIDIA drivers are installed on the compute node, and those have to be plugged into the real physical GPUs. So they can't be in the container. Because if you pull the drivers off of one machine and put them on another machine, they will be configured incorrectly. They'll be looking for the wrong GPUs. So the drivers are the closest to the GPUs. They need to be on the compute node. The drivers are not in the container. Also, they're probably proprietary. I don't even know. But CUDA is available for everyone to download. So you can download the CUDA development kit, put it in the container, and build your software. And the only thing that's missing from the development kit is the drivers. So there's a very consistent split there, and you can't really mess it up. So in order to use a GPU, you have to get a GPU node. So this is the interactive command line method. You can also use the Jupyter Notebook method from the on-demand portal. I think they both work. Let's do the command line method first. So we need to get onto a GPU node. Relative to what we did before, that means you need to add two flags. The gres equals GPU1, which is the Slurm directive for I need one GPU, please. And partition equals GPU, which is the Slurm directive for I need to be on one of the nodes that has GPUs. And those are actually two different things. Requesting access to a GPU and requesting to be placed on a node that has GPUs don't actually necessarily go together. There are GPUs in the reservation, so I believe we can use the short course reservation along with these flags. We're going to try it and make sure it works. I don't want to leave you all hanging. I'm copying and pasting one line at a time so I can make sure it all ends up on the same line together. Because when you copy and paste multiple lines, you get kind of random results. And I want to try the short course reservation because, oh, I know what I did wrong. Okay, you have to read carefully. It says from the login node. So you can see we're currently on a compute node. I'm currently on AC77. We forgot we needed to do this from the login node. So I'm just going to get a fresh login node because I don't want to give up my other terminal. We might need it. So let's try that again from the login node. So we'll copy this, paste it here. Oops. See, that's what happens when you try to paste more than one line at a time. Doesn't work. pty-i. Oh, that's because I have a stray character. I'm really frazzled. I apologize for being really frazzled. So I think this is what my command was always meant to look like, right? Yes, and now it's working. So the command wasn't wrong. I just forgot you have to be on a login node. Okay, so there are 4 GPUs in the reservation. So 4 of us can do this at a time. It looks like there's already maybe 4 people on there. Yeah, so it looks like there are 4 H100s available in the reservation, and they're all being used. Oh, and one of them is being used by me. Ah, there we go. Okay, so if you're in Zoom, if you want in Zoom and you say, I wanted a GPU, but I didn't get one yet, go ahead and speak up in Zoom and we'll make sure everybody gets a turn. So currently it looks like SS, MG, YC, and RL are on the GPU nodes in the reservation. And that's me and then 3 other people. But everybody can have a turn. So we'll wait to make sure everybody gets a turn. Now, what were we meant to be doing today? We're meant to be doing Singularity exec --NV and the PyTorch. So where's the PyTorch again? The PyTorch is in Scratch training Singularity, right? So we need Singularity exec --NV PyTorch. And what was the command we wanted to execute? Python 3. So you can either include the Python command after the -c, or you can just do it interactively. Import torch, print torch dot CUDA dot, what was that command again? Device count. Anybody here familiar with Python? Oh, I'm in the wrong prompt. Oh my goodness. Look, this is me on the node that doesn't have GPUs. I'm being silly. This is me on the node that has GPUs. CD Scratch training Singularity exec --NV PyTorch Python 3. Import torch print pytorch.cuda.device count 1. Okay. Everybody see that 1 on my screen there? That means PyTorch found 1 GPU. I'm not actually an expert in PyTorch, so I'm kind of stuck here. I don't know how to get much farther. We do have some colleagues who are experts in PyTorch, so if you want to learn how to do PyTorch things, we've got you covered, just not today at this moment. So what we learned was, if you actually follow the directions and you are on the node that has the GPUs, yep, there's an H100. See the H100 there? So if you follow the directions and you're actually on the node that has the GPUs, you can do import torch in the container and find the GPU. What was necessary? The exercise was, the point of the exercise was the --NV flag. Where did I put it? There it is. There's the --NV flag. That was what we were meant to be learning. And I got distracted by clicking on the wrong tab in my browser. Apologize for the confusion. So how about people in Zoom who also want to do this exercise but haven't had a chance because you didn't get onto a node with a GPU yet? So I left that node so someone else could get on, and it looks like user MG, a different MG, got on instead. So there's at least one person on that node now that wasn't there before, I think. And if you have done the exercise and you're satisfied, please do use exit to leave that node so the next person can try the exercise. If you're not really familiar with PyTorch because you're not here to do machine learning, feel free to skip the exercise. I had 2 scientific workflows I wanted to talk about today. The next one is LAMMPS. So LAMMPS is a molecular dynamics code. I'm also not a chemist, but I know a little more about LAMMPS than I know about PyTorch. My favorite thing about LAMMPS is the animated logo. So if we click on lamps.org, you hover your mouse over that logo, and the atoms move around. That's just too cool. I cannot get over how cool that animated logo is. And similarly, NVIDIA has GPU-ready container images for LAMMPS. So if you search for LAMMPS in the NVIDIA container registry, you will see this particular exact version of LAMMPS is the only one that works with H100 GPUs. Recall, in order to function correctly, the container image has to have a new enough build of CUDA, and they don't build LAMMPS all the time. Like, they build PyTorch all the time. Like, every week there's a new PyTorch. LAMMPS, they build more like every 6 months. So this is the only version of LAMMPS that's new enough that it works with the H100s. And similarly, yesterday I pulled a fresh copy of it, and it's in the training area. So we have LAMMPS, and the version is, and I named it NV because we also do have LAMMPS for CPUs. So this is the LAMMPS from NVIDIA, and its version is patch 15 June 2023.sif. And it's located in the training area. So if you want to do this exercise, you need to be on a GPU node. So same thing we did before. You get on a GPU node. You can hit the up arrow to get back there if you previously got on the GPU node. So that's, I will make sure I'm on the login node. I'm definitely on the login node. And now I can try to get on the compute node. This one, I think, right? Okay. And now I am on a compute node, and does it have GPUs? Yes, it has the H100. So I need to be in the Scratch Training Singularity directory to find the files. That's this image and also the benchmark.sh and also the lamps input file. So currently I'm in my tutorial directory. So I need to make a copy of that lamps image. So I'm going to copy scratch. Oops, I have a variable for this, don't I? $training. Lamps. I'm going to copy that here. I'm going to copy the benchmark.sh here. And I'm going to copy the lamps input file in.lj.txt. Those are the three that I need. So once you have those three files, lamps, benchmark, in LJ.txt, then we are ready to try lamps. So the syntax will be Singularity run. And you might be thinking, but wait, Richard, aren't we going to be executing a specific command, benchmark.sh? Yes. However, in order to execute lamps in this container image, we will need to set some environment variables that NVIDIA knows how to set and we don't. And the way that NVIDIA decided to do that is they made their run script, the default run script for this image, to be a wrapper. A wrapper means it executes commands and then it passes control back to the user to execute the next command. So we're going to do Singularity run --nv lamps tab autocomplete. And what run is going to do is it's going to execute the default run script, which sets the environment variables. It finds which GPU, finds which build of lamps, match them up, set the correct environment variables, and then pass the control back to you, the user. So it essentially becomes an exec command after doing its run thing. How do you know? The only way to know is to have the developers tell you. So we read the documentation, and the documentation explains how to do it. And then you're free to do your whatever command you want, bash benchmark.sh. Anybody here familiar with lamps? Do you know how to read the output files? It says, we'll use up to 1 GPUs per node. So it successfully found a GPU, and it computed at a rate of 919 million atom time steps per second. If you're familiar with lamps performance values, this is a very high performance value. You cannot get 919 million atom time steps per second on CPUs. There's no CPU powerful enough to do that. So this definitely did do using the GPU. GPU made it fast. It was like, how long did it take? Less than a second. CUDA module loading equals lazy. Someone asked a question about CUDA module loading equals lazy. So NVIDIA is kind of funny. Whenever you load NVIDIA software, whether it be PyTorch or LAMPS or TensorFlow, the first thing CUDA is always going to want to do is check if there's a GPU. If there's no GPU, it will complain and say, look, you brought me here to use a GPU. I don't see a GPU. I can't do my job. We're done. And then we'll abort your mission. CUDA module loading equals lazy is basically saying, we're going to defer that operation until later. So instead of right now check if there's a GPU, just put the software in memory and we'll check if there's a GPU at a later time. The advantage of this is if all you want to do is test if the software exists, like Python import torch, you can import torch in lazy mode without doing the check to see if there's a GPU action, and then it won't fail just because there wasn't a GPU. So you can tell the difference between it failed because torch doesn't exist versus it failed because there wasn't a GPU on this node. So CUDA module loading equals lazy helps you, helps you to tell the difference between the software didn't load and the software loaded, but there's no GPU on the hardware. If you don't have CUDA module loading equals lazy, then CUDA will always check for hardware first thing and fail, and you would never find out if the software was installed correctly or not, because PyTorch wouldn't even get as far as loading import torch. It would just immediately abandon all hope, and all you would learn from that exercise is there's no GPU on the node. So I guess the NVIDIA developers decided to let us be lazy this time. I don't know. I'm not really in charge of that. So we have reached the end of our time, which is good because that was our last exercise. So I'm going to read my acknowledgement slide. This work was supported by the National Science Foundation, award numbers 2112356, ACES, Accelerating Computing for Emerging Sciences. This grant paid for the ACES test bed, so all the nice H100s, including the ones that we tested today. Let me abandon my H100 now, so in case somebody else is waiting to use it. PE Stat R short course. Okay, so some people are using the GPUs. You can have time to finish your exercise. I got off the GPU. If you're done with the GPU, please get off so someone else can use it. Yes, so ACES grant paid for the nice GPUs, including the H100s we played with today. We also have the Sweeter grant, Southwest Expertise in Expanding Training Education as Research. Sweeter pays for the time of our educators like me to do these training activities so that you can have someone to talk to instead of just reading the manual. We also have the Faster grant. Faster is another cluster we have. Many of our training materials were developed for Faster, so some of what we have for you today is recycled material from that grant paid for. Finally, I need to thank the staff and students at Texas A&M HPRC. For example, our help desk worker Druva, who launched our Zoom meeting today, our system administrators who got us that short course reservation so that we would be able to use H100s for our exercises. And finally, the ACES CSEP pilot program. Previously in the semester, I taught some different container courses, and one of those received a grant from the CSEP pilot program, which means that someone will get to go on an expenses paid trip to the supercomputing conference, and it's me. So I will be in Denver in November, thanks to the ACES CSEP. And although that was for a different course, some of the materials are recycled. So, thank you to ACES for helping to make some of the materials possible for this course. So this is the last slide in my slide deck that says, here's how you contact us, help@hprc.tamu.edu. If you have questions about how to use Singularity on the ACES cluster, or you want access to more training materials, you can always ask. And since we do have grants like Sweeter, we can often spend our time to help you, even if it's more than just, my job crashed. Why did my job crash? So feel free to ask all kinds of questions that you have. But if you are asking help for technical support, please do provide lots of information about what you're trying to accomplish so we can figure out how we can help, who we need to assign to help you.